Hello, welcome to Everything Distributed. Today we are going to continue on consensus and with a cross failure in asynchronous systems. Recall that last time we discussed about this very cool result of fundamental limitation in distributed system, meaning the FLP impossibility. And in order to circumvent this impossibility, we need to relax our model, either a network, termination, agreement, or any other kind of assumption. And today we are going to focus on number 3. We are going to relax our agreement problem. So we have a new type of consensus problem called approximate consensus or approximate agreement. So what is it? Recall that the traditional consensus definition, now here we call it exact because of the agreement property. Here, we want each node that have not crushed yet to output exactly the same thing. So we have this exact consensus. But this is impossible to achieve. So we relax our property, say that now the agreement is at roughly the same output and all the other properties the same. And this is called approximate consensus. Okay. You might think that, okay, in many of the applications, this is not really useful, but it turns out that in control system, distributed robots, and lots of IoT application, or even like the clock synchronization problem, approximate agreement is also very useful. And from now on, we also assume that we have n strictly greater than 2f nodes. So remember what's f? F is the upper bound on the number of faulty nodes in our system. And in this case, we need to have at least 2f plus 1 nodes in order to solve approximate consensus. And here is the algorithm is actually very simple, only 6 steps. And one important notion to remember is that because we are in a synchronous system, and every node, they may not proceed in the same time. And then in the literature, we call this thing as a asynchronous run. So that even though it's very different time, but like we can have this artificial run, and then each run is marked by a run index. Okay. And the other thing is that our channel, remember that from, I think 2 times ago, that we talk about our underlying channel. Here, we assume that the underlying channel is reliable. And then we use like this unicast thing to send our message or to multicast our message to all the other nodes inside the system. Okay, so let's do the initialization. Here we have yi, where yi is the state variable, which is a real value that you represent the state of you right now, and eventually this yi will be your output, and where xi is the input that's given to node I. And this R is the run index, R equal to 1 initially. And because this is a synchronous run, so my R1, my first run may happen at a very different time at your first run. So it's possible that for right now, at this point, I'm at run 100, but that you are at run 10. It's totally possible. And then the way you send the message is that you still do this multicast thing. You send the message yi, your state value, and also the index, the run index to all the other processes or other nodes, including yourself. And then you just wait until n minus f message. So remember what's f? F is the upper bound on the number of nodes that might fail. Then you just wait that, okay, this message must be at the same run. And if I receive them, then I can proceed to the next step. And then the next step is that for all the values that I have received, I just take the average. Okay. And then when I take a value, average is I only consider the first field. I just remove the R, okay? Then the fifth step is how you update to the next run. Then the sixth step is how you go back to step 2, then send R again. And then that's all, okay? And then one key thing to remember in this kind of a synchronous system, in order to ensure liveness, meaning that you must be able to make progress, is that at any point of time, you can wait for at most n minus f messages. And that's why we need to have this n minus f. So suppose you want to wait for all n messages, is that possible? I mean that if your algorithm is designed like this, can you make sure that your algorithm can always make progress? And the answer is no, because if any of the nodes crashes, then you got stuck. And that's why we need to have this n minus f things here. And then if you look at lots of algorithms in the distributed computing literature, especially the fault-tolerant one, this n minus f things, this threshold will appear again and again, okay? So very simple algorithm, but why is it correct? And the first thing you might ask is a termination. You just keep doing this while looping, you never terminate. And actually that's pretty easy. I didn't state it because you can specify a fixed number of asynchronous run in the system. And then you can say, okay, suppose I want to do 1,000 runs, then I can always terminate at that time, okay? And then the next thing, remember, was validity. Validity is that your output value cannot be too far away from the input value. To be more precise, it must be inside a convex hull, okay? Then this follows from the way we update our value, because we always take average. So by this kind of math property, your new outputs or your new state will always be inside a convex hull. And since the output must be must be your state, so validity is satisfied. And then the agreement or the approximate agreement is the slightly tricky one, but once you set up the definition correctly and properly, it's actually very simple. So now we consider any two nodes ij and some run t, where ij just the nodes that they have not crushed in run t. And then let's define rit as all the value that receive at I in t, and similarly for rjt. And remember, we assume that this node have not crushed at the end of run t, so they will update the state, I think in step number 4. Okay, so now this YIT and YJT are also well defined. And then the key observation or the key claim that you want to make is that this RIT intersection RJT is not empty. Okay, so to intuitively, here is that this is my RIT, and then this is my RJT. And then I want to show that this part is actually not empty. Okay, so that is the key claim. And why is it true? The reason is actually by a very simple counting. The two observations we want to make in order to prove this claim is that first, by assumption, n is strictly greater than 2f. Okay, and then the second one is that for each circle I draw here is actually contains n minus f messages or n minus f values. Okay, and then I will leave this as an exercise to show that actually I can show that there is some value in the intersection. Okay, and then once I prove this key claim, actually the agreement is very simple. What you want to show is that because no I and no j, they will always use the same value. That value will contribute to their new state, And then this is enough to show that for any pair of node I and j, if they have not crushed it yet, their difference between their two values will be smaller and smaller. And then if that t goes to infinity, actually this thing will approach to 0. And then that's all we need to show that it achieves the approximate agreement. Okay, and that's all for today. Thank you.